Okay, so now we're going to talk about enthalpy. Enthalpy is going to be represented by a capital H. All right, when we're dealing with enthalpy, we're going to focus on the heat side of things, and we're going to kind of ignore any work associated with these things. Okay, when we're dealing with thermochemistry, a lot of times we're just worried about the heat coming off those reactions. In this case, we're going to have delta H then is going to be equal to Q sub P. Now, delta H stands for that change in enthalpy for a process. Remember, delta represents final minus initial, so delta H could also be H final minus H initial. Q sub P is going to be the heat lost or gained at constant pressure. That's all it means. So delta H of an overall process equals H final minus H initial, which is going to be equal to the heat lost or gained in that process. For a chemical reaction, we write it as delta H of reaction is going to be equal to enthalpy of the products minus enthalpy of the reactants. Products are our final state, reactants are our initial state. And that difference in enthalpies is going to be equal to the heat lost or gained by the reaction, so Q of our reaction, Rxn. Let's look at some enthalpy examples and a few more definitions. First example we're going to look at is something dealing with an exothermic reaction. Well, an example of an exothermic reaction is a hot pack. So hot pack is going to be a reaction of Fe and O2. With those hot packs, they've got really fine particles of iron, and they're reacting it with O2 from the air. And it's going to go through this process. Now when we look at this, if I start with my iron and oxygen, that's my initial state for this hot pack. As it starts to react, I form the iron oxide, or rust. Okay, well, rust is a much more stable state than the iron and the oxygen by itself. So I go from that higher enthalpy to a lower enthalpy. In order to go from that higher to lower, something has to be lost. So when I think about this, if I'm going from a higher enthalpy to a lower enthalpy, are we going to have heat as a reactant or a product for this process? Well, we have to give heat up. The heat has to come out of that system. That's how we're losing this energy. So if we're doing that, then the question also becomes, is delta H going to be greater than or less than 0 for this process? Remember, I'm looking at final minus initial, so if my final enthalpy is lower than my initial enthalpy, for this process, delta H should be less than 0, or a negative value. So with exothermic reactions, I end up with delta H's that are negative, and that means heat is a product, and I'm giving heat up from this reaction. Okay, if we look at the opposite of that, we can look at something called an endothermic reaction. So this could be a cold pack for dissolving ammonium nitrate. Now technically this isn't a chemical reaction, it's a process, but it's going to help us relate this idea to heat lost or gained. Alright, so if I take ammonium nitrate solid and dissolve it into ammonium aqueous and nitrate aqueous, so if I look at a picture of this, my initial solid has a lower enthalpy than my ions dissolved in solution. So in this case, is heat going to be a reactant or a product for this process? Well, in order to go from this initial lower enthalpy state to the final higher enthalpy state, I have to put energy in. So I have to put heat into the system. Well, if I'm adding heat, that's going to be on the reactant side. So in this case, for an endothermic reaction, one of the reactants would be heat. Is delta H from this process going to be greater than or less than 0? Well, if my final state is higher energy than my initial state, final minus initial in this case, means I'm going to have a positive delta H, which means it's going to be greater than 0. So if I have a positive delta H, that means I'm absorbing heat, I'm taking heat in from the surroundings, and I've got an endothermic reaction. When thinking about these heat transfers, though, these exothermic and endothermic reactions, keep in mind, we're talking about an actual transfer of energy. Okay? They're not absolutes. When we say something feels hot, it feels hot because we're getting energy transferred from the system to the surroundings. When something feels cold, we're getting energy transfer from the surroundings into the system. So when your hand touches the cold pack, heat from your hand gets transferred into the cold pack. Okay, you need to understand that concept of this transferring of energy. All right, let's look at some processes here. For each of these, we want to think about, are they exothermic or are they endothermic? Remember, exothermic, we're getting heat out of the system. Endothermic, heat's being absorbed by the system or taken into the system. So if I take liquid water and I freeze it, is that exothermic or endothermic? Well, if I'm starting with liquid water and I want to cool it down, what has to happen? That liquid water has to give heat up. So freezing liquid water means I'm going to be taking heat out of that water. It's going to be an exothermic process. What about when I take that ice now and that ice gets warmer and starts to melt when you touch it? Well, that's an endothermic process. The ice is absorbing the heat, causing it to melt and get warmer. Water boils in a kettle being heated on a stove. Well, if we look at this then, inside the kettle is our system. Water boiling, that's actually an endothermic process. Why? Well, because we're putting heat in, right? We're heating the water. Now you may think that doesn't make sense because if you put your hand in the boiling water, it's going to feel hot. Well, that's because when the water touches your hand, it starts transferring its energy to your hand. That's an exothermic process. But when we're heating that water, we're putting heat in. That's an endothermic process. All right, water vapor condenses on a cold pipe. Condensation is the opposite of boiling. So in order to go from the gas to the liquid, we have to give up energy. That would be an exothermic process. And the heating of a car engine as fuel is burned. The heating of the car engine itself is going to be an endothermic process. That car engine is absorbing that heat. It's taking heat into it from its surroundings. Burning the fuel, well, that's going to be an exothermic process. And with that exothermic process, as that fuel is burned, that heat coming from that exothermic process of burning the fuel is going to the endothermic process of heating the car engine. Okay, we're getting that transfer of energy from the fuel burning to the engine. Now, when we get to chemical reactions, we're going to talk about something called enthalpy of reactions. Thing to keep in mind, enthalpy of reactions is going to be an extensive property, which means it's going to depend on the amount of material you have. When we write these out, we're going to have our balanced chemical equation, and then to the side of it, we're going to have our delta H value. So in this case, CH4 plus 2O2 gas goes to form CO2 gas plus 2H2O. That delta H is going to be equal to a negative 802 kilojoules. Now, the fact that it's negative means that it's an exothermic process. Okay, now, because it's an extensive property, if I do this reaction twice, I get twice the amount of heat produced. Now, the heat lost or gained in this chemical reaction is also going to depend upon the direction of the reaction. So if we reverse that reaction, so in other words, if I go from the CO2 in the water to the CH4 in the O2 gas, my delta H now is a positive 802 kilojoules. It's an endothermic process now. So when I flip that equation, I take the opposite sign of what I had. So CH4 is methane. If I burn methane, I get energy out. Theoretically, if I wanted to get that methane back from CO2 and water formed, I'd have to put energy in to get that methane back. Now, another thing to keep in mind when we're dealing with these enthalpies of reaction, the change in enthalpy is also going to depend on the state of these materials. So if I look at gaseous water going to liquid water, well, that's condensation, right? Going from the gas phase to the liquid phase, that's condensation. That's an exothermic process. How do I know it's exothermic? Well, I've got a negative delta H value. The states of these things are going to be important. You need to pay attention to the state they're in. So if I look at that previous example, I had gaseous water in that previous example, and it was a negative 802 kilojoules. Now let's say I take my reaction, and instead of having gaseous water, I have liquid water. Well, the delta H for that reaction is a negative 890 kilojoules. Why? Well, to go from those 2 moles of gaseous water to 2 moles of liquid water, I have to give up an additional 88 kilojoules. So if I add the negative 88 kilojoules to the negative 802 kilojoules, I get my overall negative 890 kilojoules. So with these enthalpies and these reactions, states are going to be very important because changing the state is going to change the energy. All right, lastly, we need to know some important types of enthalpy changes that we're going to run across. And you need to know by definition what these mean. So we're going to have a heat of combustion, which is represented by delta H of combustion, or COMB. Delta H combustion, it means we're going to burn something, it's going to react with O2, and our products are going to be CO2 and water. Now with heat of combustion, it's for 1 mole of the compound reacting to form CO2 and water. So the heat of combustion we're talking about here is the C4H10. We only have 1 mole of it, which means we have fractions in our balanced equation. Before we've said we can never have fractions, but in this case it's the amount of energy required for 1 mole of C4H10 to combust. Okay, so we don't have to have a whole number equation here. All right, let's look at another one of these. We have heat of formation, so delta H sub F. Heat of formation is going to be the amount of energy required to form 1 mole of a compound from its elements in their natural state. KBr solid, I've got 1 mole of it there. I have to form it from K solid and Br2 liquid. Remember, bromine is a diatomic element. So in this case, I once again have a fraction because I need to end up with 1 mole of my compound. I have heat of fusion, which is delta H sub FUS. Well, that's the amount of heat required for 1 mole of our compound to go from the solid phase to the liquid phase. Okay, that's heat of fusion. Heat of vaporization then, which is delta H sub VAP, is the amount of heat required for 1 mole of our compound in liquid form to go to 1 mole of our compound in gaseous form. Okay, so you need to recognize these different types of enthalpy changes. You need to be able to identify them as the heat of combustion, heat of formation, heat of fusion, heat of vaporization, and you need to recognize that it's for the 1 mole of the compound and it's related to the amount of heat either absorbed or given off in that process. Alright, so that's covering the basics of thermochemistry.